Okay, I think we have something now. Am I live? Welcome, everyone. Sorry for the delay. I'm Ed Pegg Jr., and this is talk 24 in my series on mathematical games. This is a homage to Martin Gardner's Scientific American column, which he ran for 25 years and published 15 books on the topics. And today I'm going to be talking about things related to cards, set, dominoes, spotted, Scrabble, and other items. We have many demonstrations that deal with cards and card-related items. It's not just the search cards that finds things, and we'll be talking about some of these today. So first, I usually talk about things that are in the news that have happened recently. One thing that just got solved recently is the haberdasher problem, which Gartner talked about several times, where you cut a square into minimal parts so that they can be rearranged to make an equilateral triangle. Well, that was sort of solved by Dewdney 122 years ago, where he published this solution, which divides a square into four parts, which reassembles into an equilateral triangle. But it's long been an unsolved problem whether you could prove that four pieces was the minimal. And just last week, there was finally a proof by Eric Demain, Tonan, and Ruehe. This is the archive paper. And it's rather long and elaborate. This is turns out to be a very difficult problem, and they did not manage to solve the problem for whether you can flip the pieces or not. So that's still an open question, but everyone believes that four is the minimal in either case. So that problem has finally been solved. And the community post we had here also claims that this shape is the smallest or is the largest possible sofa for the sofa problem, what's called the Gerver sofa. So those are two items that have been in the news this past month. One aspect of cards is that Martin Gardner talked about these related items a lot within his columns and books. And this is one of the few topics where every single one of Martin Gardner's 15 books covers cards in some form in the course of the book. And I'll be talking about many of these. Some of them I don't have. For example, the ternary system. I've tried to develop a card game for balanced ternary, but I wasn't able to get it to work. And so I don't show it here. I don't have a NIM here, but many of these others I'll be touching on today. So the first thing you might think of for card games is a standard deck of cards. So one way of thinking of that is a 4x13 rectangle, and you can tweak the deck in many ways, like you can toss out all the aces for a 4x12 deck, and there's many different games that modify the deck in various ways. You can add in jokers or wild cards, or you can make pinochle decks, which throw out the low cards, and so on. With specialty decks such as Solitaire for Two, Trumpet, Sextet, Lynx, Empire, they introduce new suits. Usually six, but five suits is common. So here's a set of cards for Solitaire for Two. And Rummy Cub tiles are basically the same as playing cards. They use the numbers 1 to 13 in 4 colors. And there's many different card games that Martin Gardner discussed, including Ulysses, where you have cards played with a particular rule, and there's a person who knows the rule and starts laying down cards, whether they follow the rule or don't follow the rule. And for example, in his column, this set of cards follows a particular rule that people need to figure out. The next set of cards people know about, or tiles, I use cards and tiles interchangeably, is dominoes. And the most common set is the 28 double six tiles. The number of dominoes is a triangular number. We can see that by doing the tuples that are possible, and then comparing that to the actual triangular number, and they're identical, of course. So there's 28 order 6 tiles. Those are everything from 00 to 66. My favorite set is the 99 set. Everything from 00 to 99, and that's also frequently available as cards. And if you look for 99 cards, you can find them. You can also get rid of the double and zero tiles for various games, such as what Kaylee did here, using a double 8 set without zeros and without duplicates, and he used that to solve the Kirkman schoolgirls problem, which is shown here. This is actually Kaylee's solution. I just made it look fancy. 7 I think is a more interesting set with 36 dominoes, so that's a nice square number. 14 with 120 cards is nicely divisible, so that might be a more interesting set. I'm not sure why they picked 15 or 18, but you can always get a 15 set and discard some. There's also different ways of doing the pips. For example, here's a 7 binary coded hex dominoes, and there's 36 of them, where they use this would be 1, a blank would be 0, the larger circle would be 2. These are all encoded in binary. So there's a lot of different games and puzzles you can do with dominoes. For example, you can lay them out in a grid and try to figure out how to divide the grid up into a working set of dominoes. And these are non-trivial puzzles to solve. So when you're dealing with building a mathematical set of cards that is different from the normal sets, one of the first things you need to decide is how many cards are in your deck. Richard Garfield developed Magic the Gathering, which I curiously helped him with. I was doing an art magazine back then, and he hired a bunch of my artists to do the art for the initial deck. It now has almost 100,000 different cards in it, and that's a few too many cards for a nicely playable game of cards. I have no idea how much it would cost to buy all these cards, probably a lot. As a general rule, I aim for 21 to 121 cards. But if you want to shuffle them, you probably want to stick with 40 to 70 cards. More than that, it starts getting tricky to shuffle. It's also convenient to hit nice numbers, which I'll show down here. And many purists want a complete set. If a game is, say, based on square numbers to 36, then it really should have all of those numbers. Otherwise, you're talking about a property, but you're throwing out some of them arbitrarily. It also helps if the cards are fair, where each card can have equal power. For example, aces and kings rank higher than other cards usually. Ranking also works very well in some games, but mathematically it's better to keep everything fair. So here are some nice numbers to hit for a deck of cards. Factorials grow too quickly, and many wind up being based on triangular numbers, for example, double nine dominoes. 66 is the number of octominoes, coincidentally. And if you have any of these, you can at least have often games. For example, with the 5 smooth numbers, you'll be able to usually hit players, 2 to 4 players, without any cards being left over. But being one off, having 1 card left over, that can also be good. One type of game I took a look for, but I didn't see good evidence of them, is having a modulus-based game. If anybody knows of a modulus game, I'd like to hear about it. For example, that would be where 13 beats 12 through 7, and 7 beats 6 through 1, but 2 beats 1, and also 13 through 9. This would be a way of making cards fair, but I haven't seen anybody do this. This would probably work better with rummy cub tiles than normal cards, because you'd also have to remember Jack is 11, Queen is 12, King is 13. Or no, no, that's not right. Yeah, well, Ace would be 1, right? So Ace would, if we use mod 13, Ace would be both 1 and 14. The next set of cards that usually comes up is the colored squares, where you have all the different ways of coloring the sides of a square with 4 colors. Or is it 3? I think it's 4. Yes, 4 colors. And these were looked at by Percy Alexander McMahon, who also looked at coloring the edges of triangles in different ways. And these are pictures from Gardner's column on the 2 different sets. Catalan Enterprises now sells many variations of these 24 pieces. It's 24 for both the squares and the triangles. Oh, and it's for squares, it's 3 coloring the squares. With 4 colors, you get to 70 pieces. I haven't seen a 70 tile set though. So these are different ways of doing the squares and the triangles to build these 24 different patterns. And here's with triangles, it's 4 colors. You get this set. If you go up a color, you get 45, then 76. We can also look at coloring hexagons, but those grow very quickly. With 2 colors, you have 14, but with 3, you're already up to 130. So 45 is probably a good tile set for triangles, and I believe 76 triominoes is quite common. This also scales up to colored cubes, but I haven't seen too many people, at least any time recently, building a set. These were known as Mac-Behind cubes, but I haven't seen too much done with them since Gardner wrote about them. Now, one curious thing Gardner mentions in his column is to get the number of pieces that you would have. You basically just take the number of faces factorial and divide by twice the number of edges. So f factorial divided by 2e, which is something I think I knew, but I forgot. And when I was reviewing for this column, I came across it again. So these are the number of different octahedron cubes you could make, and this is way too many icosahedra. So cubes is where you want to go for coloring sides of a polyhedron, but I haven't seen too many people work with those 30 cubes. Binary is a good set to use, especially 0 to 43. These are the, what are these? The hexagrams, and these were looked at by Leibniz he thought he developed the binary system, but then he found that a person in China had done the same thing earlier with these. The game Check It uses binary with these hexagonal tiles. And basically the way they're encoded is it's basically fixed so that a dot is at the top of all these numbers, unless there's a lot of symmetry. In that case, they throw the dot out. But basically you get all the numbers 0 to 63 as a coloring on the tiles. And it's a nice set, but I haven't seen too many people use the Check It set. You can also do 6 dots on a card. They don't have to be colored. You can also use black and white. You do need to keep track of which direction the cards are, because if you rotate them, you can get a different number. So usually what I would do is I would cut one corner of the cards or something just to indicate which direction is up, so that you have the 64 or 63 cards arranged correctly. Usually you want to throw out the blank card, but it's okay to keep that in. So one game you can play is binary XOR. So let me just pick something randomly. What you want to do is find any number of cards so that when you add them together in binary, each position has an even number of white or black spaces. So for example, for this one, sorry, these are the solutions. So that 53 and 58, what was that one again? 53, 58, oh, that one. 53, 58, and 15 have a even binary sum, these three. And these 4 cards together. So this is a rather tricky game. There's always a solution with if you use 7 cards at each time, but it can be very tricky to actually find the correct solution. There's also permutations. This is a game called Flix Mix, where you basically have cards and you need to copy the color dots on another card as you're laying them down. And you always have to copy at least 2 color dots when you lay down one of your cards. However, this isn't a complete set of cards. The number, if you wanted a complete set, you need to have 180 cards. So here's a set of random Flix Mix cards that could be played. But I think that's too many. However, if we scale this down to hexagons, we get 60 hexagons, which could be played in the same way. So I think this might be a good set. The 60 requires you have to be able to flip, so you want to make these with clear tiles. So this might probably be a very nice set in hexagonal lucite, where you have all 60 combinations of these hexagons all sealed in lucite. But that would be expensive to make. There's also word-based cards where you use letters on each tile. Scrabble, of course, is well known. That's the distribution, and we can get a random set of letters. So that could make I'm blanking on a good word for those. Boas, but I'm sure there's someone who can come up with a better word than boas. Anagrams and bananagrams uses a different distribution with more tiles. Usually 15 tiles are handed out, and you can reuse the the tiles to make crossword-like arrangements. So for example, you might get this set and you need to be the first person to complete a crossword-like grid of words. One thing I've played with is a international phonetic variant, but it really didn't seem to work out because I don't know how to spell phonetically all that well. For example, if you gave me a minute, I still couldn't probably do International Phonetic Alphabet correctly. So since I don't have enough familiarity with how things are spelled phonetically, even though I can slowly figure it out, it's not good for a game setting. So for example, I don't know what words I could make with this, but I guess tune would work, but tune probably doesn't use the E, so that wouldn't be a valid word. There probably is a T, some vowel N word that could be made with these. Probably all of them work, but I'm not exactly sure what they are. There's also the game Set, which is based on powers of three. It's the Z3 set, where basically you pick 4 different properties, each with 3 items in that property. So for example, they use 3 shapes, 3 shapes, 1 to 3 items, 3 colors, and they can be empty, shaded, or solid. So those are the 4 different properties, each with 3 elements. And it turns out you can make all 1080 sets as a series of sets using 40 decks of cards. You can do all the possible sets in set. And this is a demonstration, the set of sets and sets, if you want to look at the Wolfram demonstration. So this is a very nice application of projective group 3-4. And I've played quite a few games of it, but I haven't come up with additional games other than the standard set game. I need to look at that one more to see if I can figure out other games that could be played with that deck. Another well-known game is Spotted, where you hit 2 cards. For example, these 2 cards here each share a pencil shape. Basically, you lay down cards and you have to spot the one item shared by both cards. However, it's sold as a set of 55 cards, but there's actually 57 cards in the full mathematical object that this is based on, which is the Springer difference set, or also called the Ganymede circle or the in switch. And here's the 57 difference set that is based on, where basically you add into these numbers up to 57 and then take the modulus 57. Let me talk about a smaller one first. This is the order 31 set here. And it's called a difference set because if I look at all the different subsets of these numbers, there's 15 subsets of these 6 numbers. And if I look at their positive and negative differences, mod 31, we get all the numbers 1 to 30. And that's why it's called a difference set, is because if you with a particular modulus, it gives all possible differences. So for each of these, that is a property. For example, with the modulus 91 set, all the different subsets of 2 items give a complete set of numbers 1 to 90. But another property is that if you have 2 cards based on these, for example, if I take the 57 set and I add a random number and shuffle around the numbers, and no matter how it's done, these 2 cards will share a number. But I don't see what the number is right off. 0, 39. What's the shared number? Does anybody see the shared number between these? 40, no, 21. Oh, let's try that again. Maybe that's a wrong set. Did I set this up right? Looks correct. 29, 22, 5, 8, 52. Oh, these both share 13. This was easier when I tried this at my desk earlier. And I'm not sure what these share, but basically, no matter how you set these up, it will always share a number. I'm not sure why this doesn't seem like it's working now, or maybe I'm just not spotting things that easily. 11, 44, 46. Oh, these both share 15. And you can keep doing this with larger sets. For example, here's 73 cards. These should share a number somewhere. And you can also do 133 cards with these sets, and these two should share a number. We could go up all the way up to 381, where these two would share a number. But these appear to be harder than I can do while giving a talk. These are other ways of showing these configurations. Here's one way of doing the 21 cards as a set of circles and lines, where every circle and a line is one of the different sets in the 21 set. And here's a way of doing the 0, 1, 3, 9 different set with parabolas, where every parabola has 4 items on it, and every dot has 4 parabolas going through it, making it a configuration. Gardner talks about Catalan numbers found by Euler. How many different ways can you divide up a polygon into triangles? And these are the ones that Euler found. And he found a formula for the number of polygon triangular dissections, and these became known as the Catalan numbers because too many things were named after Euler. So these are, for a given number of sides, you can look at all the possible triangulations. And here's some code for doing that. We can take a look at the number of different triangulations. And for example, these are all the 49 nonagon triangulations you can make. So this might be an interesting deck of cards where you needed to match a set of triangulations that only had one flip in them. For example, with this nonagon, you could flip this diagonal to go over to this side instead, and somewhere in here is that flip. So looking at flips, each of these cards is connected to some set of others. For example, this one is connected to that one by this quad flipping here. For fairness, one thing I like is self-dual configurations. So for example, this set of points here is self-dual, so such that every one of these points, if you consider them in barycentrics, has 4 partners where if you multiply them, if you take their dot product, you get 0. And this is the set of 51 cards on 51 lines. For example, this line here is 112, which is over here. If you do the dot product of 112 and any of these points, for example, 1, 1 minus 1, the red means negative, you get 0. Each one of these 51 lines is on has 4 points, and each point is on 4 lines. So this might be an interesting set of points, lines to play with, and it's the sort of the right number, 51. But doing dot products in your head can also be difficult to do. The Klein configuration is even worse, but it's got much better properties. It's 60 points and also 60 planes, so that 15 points are on each plane and 15 planes go through each point. And this also uses dot products. Anytime one of these has a dot product of 0 with one of these others, they are connected. The plane is on the point, or the point is on the plane. And each one is on exactly 15 others. So here's a set of randomly selected Klein cards, and it's a very nice number, 60. Let me do that. So here's a possible layout for Klein cards, and your goal would be to just find 2 cards that have a dot product of 0. Let me see if I can spot one here. So let's see. Oh yes, so this one, dot product with this one, you'd get 1 plus minus 1 plus some zeros, so these 2 cards are connected. So this would be a very difficult, challenging game, but also has a lot of nice math properties, and everything is either 1, minus 1, 0, I, or negative I. So that might be a nice set to play around with. And the Klein configuration has a lot of crazy properties to it. A more easy set to work with is just normal numbers. One thing you can do is look for sets that add up to a particular value, such as adding to 38. And you can arrange the numbers 1 to 19 in a hexagon such that every direction adds up to 38. And the answer is unique. Martin Gardner wrote a column about this. We could also arrange coins with -8 to 8 in this pattern such that every possible triple summing to 0 is on a line. For example, 1 plus 3 minus 4 is 0. And 6 plus 0 plus minus 6 plus 0 plus 6 is 0. But also -6 plus 2 plus 4 is 0. There's all sorts of different directions that these triples show up in, but every single one of the triples is on a line. So this might be the numbers -8 to 8 might be an interesting set, but if you're looking for triples summing to 0, but 0 is the most powerful because it happens to be in the most triples. -8 isn't in nearly as many triples as 0 is. However, if we use a modulus function, for example, modulus 12, then all of these numbers would have equal value within a set. Because with modulus, you could, it turns out all the triples would have, all the numbers would be in an equal number of triples. So for more math, you can look at Krypto, or the 24 game, where you can use basic mathematical operands to add to work on the numbers. For example, if you have 2, 6, 9, and 26, here's one way of reaching a goal number of 3. 26 divided by 9 minus 2 over 6. So you have to figure out what 9 over 2 minus 6 is, and that's 8 2/3, which means 3/26. And if you divide 6 by 3/26, you get 3. So they can get tricky fast. The number of inequivalent expressions you can get from a a basic set of numbers and operands grows quickly, such as this, where you've got A plus B, A, B, C, and D. There are 68 for those 1,170 for A, B, C, D. This would be A, B, C, D, E, and so on. So one question we can look at, is there a set of numbers such that with basic operands, there's a unique solution for each of the numbers 1 to 10. And it turns out this set of numbers works. Each of these is a unique solution for hitting the gold number at the start. This is the only way to get 7 out of these numbers, unless you use something that's equivalent to it. There's various different operations of plus and minus you can do, which is equivalent to this one here. But for inequivalent, these are the only solutions for 1 to 10. Here's a few more difficult cases with these numbers getting a goal number of 5. And I've got a resource function called Krypto game, which will solve these sorts of problems. So if you put in these values for a goal number of 15, it gives you this as the solution. So just a second here. So it's easy you could get the Krypto game, but it's in sort of a terrible box. So I find it inconvenient, but it's easy to get numbered cards or tags in a variety of forms, or to make your own set of numbers on index cards. I made a game based on my favorite graph, the Hoffman-Singleton game, and it's basically triples, all triples from 1 to 7, and then a set of 15 Fano planes. So here's the triples, 1, 2, 3 to 5, 6, 7, and we can arrange these triples in this configuration so that every set of 4 triples that uses only 5 numbers is on one of these circles. For example, on this red circle here, these only use the numbers 1, 2, 3, and 4. This triple down here only uses 1, 2, 6, and 7. So this is a strange arrangement of circles, unit circles, which has all the triples, and each circle is on exactly 4 other triples, and each triple is on each circle has 4, and each triple has 4 circles. And we can also look at the Fano planes. Here's one Fano plane based on this sing or difference set, and you can vary it in 30 different ways, but those split into 2 so that each Fano plane in that set of 15 shares exactly 1 triple. So if you look at any 2 of these, there's only going to be 1 triple shared by the 2 of them. And the rule for the Hoffman-Singleton graph is any 2 triples that do not share a number, for example, 1, 2, 3 does not share any numbers with 5, 6, 7. Each triple, there's 4 other triples that they don't share with. For example, this one here doesn't have any numbers of 5, 6, 7. So this triple here is connected to these 4 triples. So each of these triples is on 3 Fano planes, and they are each also connected to 4 other triples. So each triple is connected to 7 total, and each Fano plane has 7 triples that they're connected with. A triple is connected to a Fano plane if that triple is on the card. So you get this set that makes the Hoffman-Singleton graph, which I showed here. It's a cage graph. If 2 cards are not connected, then there's a unique other card that they're both connected to. So the distance between any 2 points in the Hoffman-Singleton graph is either 1 or 2. But that also makes this big strange graph triangle free. The smallest cycle within the graph is length 5. You can't get a 4 cycle or a 3 cycle. There's no triangles. There's a lot of weird properties with this card deck. I still have a few copies if anybody wants to write to me. A similar item is the smallest projective space, where you have 15. You have triples from 1 to 15 that have a binary sum of 0. So here's the binary sums, and we can arrange them like this. Each triple is on 7 lines, and we can make 15 Fano planes out of this, much like the Hoffman-Singleton graph. But there doesn't seem to be any connection between the 15 Fano planes of the Hoffman-Singleton graph and the 15 planes of the smallest projective set. It's a different set of numbers. They seem to have different geometries. I tried for a while to make connections between them, but there just doesn't seem to be anything that works well. But this would also be a good card set to use. We can punch dots out of the border of a 3x3 square, and we basically neglect the center because there's no edge matching you can do with the center. And if you look at all the rotations and reflections, you get this set of 48 dot patterns. And these would be a nice drilled set. I made a set out of index cards. And here I do edge matching with everything that also connects the top and bottom borders. There's a left-right flaw right here. This dot doesn't match this blank here. So it's not completely toroidal, and it turns out toroidal is impossible. But you can do edge matching everywhere else and also have top-bottom matching. This is a nice human solvable puzzle if you make the set. It's slightly tricky, but there's probably quadrillions of solutions, so it's not too hard to finally nail down to a particular solution if you're solving it by hand. You can also do path puzzles. Tatrix and Calico both work nicely. This is Tatrix here. This is Calico here. Tatrix uses 4 colors. Calico uses 3 colors, but you can reuse colors. One set I made was the path dominoes. Here's a solution by Donald Knuth for using all 48 paths to make a rectangle and also a closed loop. And also I showed some solutions by Roger Phillips. You can also think of shapes as a card. The polyominoes shown here, like Tetris. Blockus is a very interesting game. And there's also a triangular variant for Blockus. The 66 octomines also make a interesting set you can play with. There's a few games that I came up with them where you basically need to make a you start with a arbitrary set of tiles, and you need to lower the number of borders on the outer shape by adding pieces to it until you come up with a shape that can't be improved, like it only has 3 sides. The heptominos also make a nice 12-color set. You can make squares out of them like this. There's various games with the polyominoes. Blockus is probably the best of them for a nice and expensive set, but Catalan Enterprises also has some very good sets. I've looked at Order 5 Ben, trying to think of a game for it, and I haven't come up with one yet, but I'm sure there's a nice game in there somewhere. This is a nice polygonal representation, and here's a set with 2 pair shapes. We could also conceivably use blocks as a set of cards. Here's a nice set with 12 blocks, each with values from 1 to 6, and each of the volumes here is 12 to 24. So these are blocks that will fit into a 6 by 6 by 6 box. These are all except the 1, 3, 5. If you take that one out, they all fit uniquely into a 6 by 6 by 6 box. Now, one possible game you could play with these is putting in, dividing up the pieces and then putting them into the box one at a time, and the less to put a piece in wins. I've tried to come up with a set of orders for almond chairs for a path game, but I haven't been able to get that to work, but I'm sure it can go work somehow. And you basically have a set of smaller cards and larger cards for the set. The clubs graph has nice properties. It splits K16 into 3 clubs graphs. So for example, this set here in 3 colors would with the 3 clubs graphs would cover all possible pairs between numbers each 4 times. But I wasn't able to make that work in an interesting way. You could also look at 56 subsets of 8 might be interesting. There's also various other 9 triples and 8 subsets, but I'm not sure those work very well as cards. The weirdest one I've looked at is the 57 cell. Now, one property is that it's based on the numbers -9 to 9 in 3 colors, with this property here. There's a lot of strange things that happen with the 57 cell, and we can either show the Peterson graphs or not. So there's these are various representations of the purple graph, and there's a total of 57 Peterson graphs that they make together. And I just couldn't make it work as a game. So at the end of this, what games might I recommend? Well, the first one to start with is a normal set of cards and a set of dominoes. And I'd recommend both Tantrix and Blockus if you want a good set of mathematical based games. And that's pretty much it, I would say, for strong recommendations. Another set you might want to do is a set of number cards. And there's many ways you can get those. Just look for numbered cards. For example, take a number cards. There's many different variants on those, and those tend to be cheaper than the actual games. So one unsolved problem, is there a great new mathematical card game that hasn't been discovered? I'm thinking that probably would be hard to do based on this next one. In gambling, can any casino adopt dice that aren't cubes? There's some great shapes for dice that are well made right now. Octahedrons, icosahedrons, the full set of gaming dice, but no casino I know of has adopted any of those dice to expand their games. So I'm not sure if anybody can get casinos to do new dice, but so the next thing up would be to come up with new decks of cards similar to some of the ones I've discussed here. So I haven't printed any new games since the Hoffman-Singleton game, but if I did, it would probably be one of the ones I mentioned earlier. The 48 domino path cards, I think, would be a great deck of cards to make. There's a lot of different things you can do with that set. The 49 8-punch square tiles is a natural set of edge matching pieces. I think those would be a very good set to have in a game to play with. Even though I don't have a game yet, I'm pretty sure that the 52 then 5 cards would be a good set. The 50 or 65 cards of the smallest projective space set would be an interesting set of cards. I'm not sure how I would set those up. but if I did do those, I'd probably reissue the Hoffman-Singleton game. But the one I think would probably be the best is the 57 cell, the craziest of them, just because it uses -9 to 9 in 3 colors. That's a great set of 57 cards, and there's a lot of different modulus type games you could do with that set. I would probably leave out the crazier math for it, but I'd still include it in some sort of weak way. It probably wouldn't be part of the game rules, but I would probably have it on the card. So for example, red -9, I would show which other 6 cards it connects to in some sort of small way. But the main feature for red -9 would be that it's red and its value is -9. So that's what I had. If anybody has any questions, post them into the chat and I'll be glad to take them. And if you have any ideas for games I might have missed, feel free to write to me. There will also be a community post for this sometime today. So feel free to post it to the chat if you have any questions, and I'll try to answer them. Any questions? So that will conclude my talk. Many thanks for joining us.